I'm going to talk today about the double pendulum, and specifically its derivation, which is done using Lagrangian mechanics, and look at its chaotic nature as a dynamical system. So we'll talk about the double pendulum itself, the Lagrangian and Hamiltonian formulations of the differential equation, and then some aspects into its chaotic nature. So this is the double pendulum. It's basically a pendulum attached to another pendulum. We assume that the lengths, the rods here, L1 and L2, don't have any mass, and there's no friction involved anywhere, so in theory it could oscillate forever. There's no external forces acting on the system. I have an animation here. The parameters at the bottom, the parameters that were used. And this runs for about 20 seconds. As you can see, it's obviously not slowing down because there's no resistance. I mean, we know in reality that eventually it would stop. So to get the differential equations, we need to first solve for the equations of motion, trigonometrically speaking. And then we need to differentiate this because our differential equation is going to be in terms of theta and its derivatives, and not the Cartesian coordinates x and y. Using the chain rule, that's where the derivatives come in. And this gives us the potential energy and the kinetic energy in terms of x and y, and we can convert that into theta as well, as we'll do in a minute. So if we replace the x and y with theta, we have the potential and kinetic energy. And then we can define the Lagrangian, which is a function of theta, theta dot, and t. Here, there's no explicit dependence on t. And it's defined to be t minus u. So this is it. It's just the difference between them. And now we're going to use the Euler-Lagrange equations. So we'll do the partial of the Lagrangian with respect to theta 1 dot and theta 2 dot, and then the time derivative of that. That term is the generalized momentum, the pi, that will be used later. And this gives us our Lagrangian system in terms, it's a second order system with two equations. And if we wanted simulations, we could stop here. These are actually the equations I used to generate the GIF up above. We could do linear analysis, we could do small angle approximations, but I'm going to keep going and go into chaos. And in order to do that, we need a first order system, and we'll do that using the Hamiltonian system. So pretty similarly, we define the Hamiltonian to be a function of the generalized momentum and theta here, and t, although there's no explicit dependence on t, to be the sum. And we can show that for most systems, this is t plus u. So we had t minus u before, now we have t plus u. And this is true because it's a conservative system, and there's some details there. So this gives us our Hamiltonian. And these are actually equivalent. So the Lagrangian system, which had dimension 2, is equivalent to the Hamiltonian system at dimension 4. And we can use these conversions. And this gives us 4 first order differential equations in terms of the generalized momentum and the position, velocity rather. And if you simulate these specifically for theta 1 and theta 2, you will get the same result as the simulated Lagrangian system. So what is chaos? Well, it's actually not just a colloquial term. It actually does have a definition. And I really like this one, which is given by Sturgatz, that it's aperiodic long-term behavior in deterministic system that has dependence on initial conditions. And the dependence on initial conditions is the most important part here, I think, because it means that if you slightly perturb the system, it will not follow that same slight perturbation throughout its orbit. It will diverge greatly. And it's also deterministic. It's not random. It's not chaotic because it just whirls around. We know its equations of motion. We can determine where it will be at any given time. So it's not random. The way that we'll show that it's chaotic is to look at its Lyapunov exponents. This is it's a sufficient condition for chaos, and there's other conditions to show as well, but those are pretty easily satisfied with our system. The idea with a Lyapunov exponent is you would measure some initial separation, your delta of 0, and you would run the two simulations forward and measure the simulation at some future time, and you would assume that the separation is exponential. And when it becomes non-exponential, you begin this again, and you start from that point. And the Lyapunov exponent is the lambda. It is the exponent. You might see a Lyapunov number, which is the natural log. So we can calculate Lyapunov exponents by using numerics. We would choose an initial condition at a nearby point with that some separation, iterate, evaluate the natural log, then readjust. So this is so that we always get an exponential model, and then keep going, and then do the average, and this is the Lyapunov exponent. There's other ways to calculate it, but this is probably the easiest for this scenario. And so what I looked at here is the Lyapunov exponent for each variable, because for an n-dimensional system, you have n Lyapunov exponents, and it's dependent on the initial condition. So when we think about chaos, we think about each variable, and we think about initial conditions. And to have chaos, we have to have a Lyapunov exponent that is greater than 1. That at least one exponent has to be greater than 1, and we can see that that's met here because we have two that are above 0. One of them will always be 0 for a conservative system like this. The other one's negative, that's fine. The point is that we have more than 1. So this is a simulation up to 100, and you could go longer, but it's pretty clear that you're always going to have 1 that is positive. But this is only one initial condition. So what if we look at varying initial conditions? Well, we can think about, let's start theta 1 and 2 from any angle between 0 and 2 pi. What is the maximum Lyapunov exponent out of the 4 that you get? So here what we're doing is we're picking off the biggest one. So here it's the blue line. I'm sorry, greater than 0. I said greater than 1. It should be greater than 0. And so we can see here that the largest Lyapunov exponent is about the center. Well, that's when the two angles are at pi and pi, which means the pendulum is straight up from its original state. So we would expect that should make sense. If you start the pendulum with a higher initial point, it should diverge more quickly. The exponent should be larger. Well, that sounds like you're just measuring its potential energy. And if you look at the potential energy for those same initial conditions, this is what you see. There's this ellipse shape which corresponds to this one in this plot. And we can see that as you go out, your potential energy decreases because one of your pendulums is starting from its rest state, say, straight down. And these are some references that we use here. So thank you.